Hello and welcome to 2.6 Derivatives and Rates of Change. The problem of finding the tangent line to a curve and the problem of finding the velocity of an object both involve finding the same type of limit. Okay, this special type of limit is called a derivative, and we will see that it can be interpreted as a rate of change in any of the sciences or engineering. Tangents. Okay, so the first type of problem we're going to be looking at is to figure out the tangent line to a curve at a particular point on the curve. Okay, and the way we go about finding the tangent is we calculate the slope of the secant line. Okay, and we let that secant line slowly approach a certain point along the curve. Okay, so slope formula, okay, this should be familiar to many people. This is similar to the slope formula we've used in high school, for example. Okay, the only difference is now we just use different notation. The idea is the same. Let's take a look at the graphic that's presented here. So we find the secant lines, as I was saying, are these lines in blue. And what we do is we approach one of the points to get closer and closer. Okay, point Q is going to get closer and closer to point P so that we can find the slope of the tangent line and then eventually the equation of that tangent line. Okay. Okay, so the tangent line to the curve y equals f of x at the point A, f of a is the line through P with the slope m equals, and so what we do is we take the limit as x approaches a of f of x minus f of a over x minus a, as long as the limit exists. Okay, so let's take a look at our first example, finding an equation of the tangent line to the parabola y equals x squared at the point P 1, 1. Okay, so what we're going to do then is we're going to use the definition that we just talked about. Okay, let me write it here. This will be the limit as x approaches a of f of x minus f of a over x minus a. Okay, so in this problem, our a is going to be the x value. Okay, so a equals 1. And then our f of x is x squared. So we have f of x equal to x squared. Okay, so we're going to plug into our equation. Okay, so limit as x is approaching a, and a is 1. And so we'll have f of x minus f of 1 over x minus 1. Okay, so now let's replace f of x. So f of x is x squared. Now f of 1, just plug 1 into our function. 1 squared is 1. Okay, so we're taking the limit as x approaches 1. Now if we plug 1 in here in the denominator, we get 0. We don't want that. So we use one of our techniques. The technique we're going to use here to calculate the limit is we're going to factor the top. Right? If we factor the top, it's a difference of squares. So it becomes x plus 1 times x minus 1. The bottom is x minus 1. Okay, we can cancel a pair of x minus 1's, top and bottom. So we're left with the limit as x approaches 1. Okay, which means that if we plug the 1 in there, we get 2. Okay, so that means our slope is 2. Okay, now our point was 1, 1. Okay, so now we could use this information and we could plug into our point slope form of the equation of a line. And then we could come up with our equation for the tangent line. Okay, so point slope form, you guys will remember, is y minus y1 equals m times x minus x1. Okay, so we have our m, our point 1, 1. This is going to act as x1 and y1. Okay, and now we just plug in and then we simplify it a little bit. So y minus y minus 1 equals 2x minus 1. So y minus 1 equals 2. We could distribute the 2. So 2 times x, 2x. 2 times negative 1, negative 2. Let's put it in slope-intercept form. So add 1. So y equals 2x, negative 2 plus 1 is negative 1. Okay, so that would be our equation of the tangent line. Okay, we sometimes refer to the slope of the tangent line to a curve at a point as the slope of the curve at the point. Okay, so if we were to take any of these curves and the points along the curve, if we zoom in enough, the curve will appear like it's a straight line. Okay, and we're trying to figure out a lot of times what's the equation of the tangent line at that point on the curve. Okay, the more we zoom in, the more the curve looks like a line. In other words, the curve becomes almost indistinguishable from its tangent line. Okay, there's another expression for the slope of the tangent line that is sometimes easier to use. Okay, so this will be an alternative version for that slope formula we used in the first example. Okay, you're just replacing x minus a with h, and then x would equal a plus h. Okay, so let's take a look. Again, this is an alternative definition. Find an equation of the tangent line to the hyperbola y equals 3 over x at the point 3, 1. Okay, so let's use this alternative definition. So we have m equals limit as h approaches 0, of f of a plus h minus f of a all over h. Okay, so our a, according to this problem, our a is going to be 3. Okay, and our f of x is going to be 3 over x. So we would have here limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. Okay, now if we plug 3 plus h into our function, we would have 3 over 3 plus h minus f of 3, so that would be 3 over 3 all over h. Now we can simplify the 3 over 3, so we have 3 over 3 plus h minus 1 over h. Okay, so what I'm going to try to do is combine in my numerator, try to make it into one fraction. So this 1, I'm going to disguise it as 3 plus h over 3 plus h. Right, so basically I'm going to multiply 3 plus h with top and bottom here. Okay, so we have 3 over 3 plus h minus 3 plus h over 3 plus h. Okay, so distribute the minus into our top. So we have 3 minus h all over 3 plus h over h. Okay, so 3 minus 3, that's gone. So we're left with negative h over 3 plus h. And then what I'll do is this divided by h, I'm just going to write that in the denominator. Okay, simplify a little further. Okay, so now what happens is we could cancel an h with the h. We're left with a negative 1. So we have negative 1 over 3 plus h. Okay, apply the limit. So we plug in 0. So we end up with negative 1/3. Okay, so that would be our slope. Now, using that information, let's come up with the equation. Okay, so the coordinate of the point was 3, 1. And we have a slope of negative 1/3. Okay, so same formula, y minus y1 equals m times x minus x1. Again, this is x1, y1, and now let's plug it in. Y minus 1 equals negative 1/3 x minus 3. Okay, distribute the negative 1/3. So we have negative 1/3 x. Negative times negative is a positive. 1/3 times 3 is 1. Okay, plus 1 to both sides. So y equals negative 1/3 x plus 2. And that would be the equation of the tangent line. Okay, velocities. Okay, so in general, suppose an object moves along a straight line according to an equation of motion, where s is the displacement, the directed distance of the object from the origin at time t. The function f that describes the motion is called the position function of the object. In the time interval from t equals a to t equals a plus h, the change in position is f of a plus h minus f of a. Okay, so we end up with writing our average velocity equation as displacement over time, okay, which equals f of a plus h minus f of a all over h. Okay, and that becomes our slope formula, right? Average velocity. Now, suppose we compute the average velocities over shorter and shorter time intervals. So as h approaches 0, right, if we take the limit as h approaches 0, now we defined the velocity, or instantaneous velocity, v of a, at time t equals a, to be the limit of these average velocities. Okay, so this means that the velocity at time t equals a is equal to the slope of the tangent line at p. Okay, so this is an important formula for our velocity function. Okay, so let's do an example. Suppose that a ball is dropped from the upper observation deck of the CN Tower, 450 meters above the ground. What is the velocity of the ball after 5 seconds? How fast is the ball traveling when it hits the ground? Okay, so to figure this out, we need to figure out the velocity when both time is 5 seconds and when the ball hits the ground. Now, one of the things we have to incorporate into this problem is our equation of motion. Okay, now in general, our equation of motion is s equals, okay, it's a function of time, which equals 4.9 times t squared. Okay, this is our equation of motion. Okay, so when we go to figure out our velocity, this would be limit as h approaches 0 of f of a plus h minus f of a all over h. Okay, so we plug in a plus h into our equation. Okay, so limit as h approaches 0 plug in a plus h, so this would be 4.9 times a plus h squared minus 4.9 a squared all over h. Okay, so now in here we have to expand on the a plus h squared. Okay, so we have 4.9 sitting outside. A plus h times a plus h, so that would be a squared plus ah, another ah, that's 2ah plus h squared minus 4.9 a squared all over h. Okay, so we have here, if we distribute the 4.9, we would have 4.9 a squared plus 9.8 ah plus 4.9 h squared minus 4.9 a squared all over h. Okay, the 4.9 a squared cancel. So we're left with 9.8 ah plus 4.9 h squared all over h. We can factor out an h. And cancel out an h with top and bottom. So we're left with 9.8 a plus 4.9 h. Okay, plug in the 0 for h. So 0 times 4.9, that's 0. Okay, so we end up with 9.8 a. Okay, so this would be the velocity function. Okay, so VA would be 9.8 a. So that means the velocity after 5 seconds would be V of 5. So 9.8 times 5. Okay, and if we multiply 9.8 times 5, we end up with 49 meters per second. Okay, so that's the first part. For the second part, we have to figure out how fast is it going when it hits the ground. So we have to figure out first what time, right? How many seconds will it take to hit the ground? Okay, so if it's dropped from this tower, right, that's 450 meters above the ground, it's gonna fall 450 meters. Okay, so we would set our equation of motion, okay, which is like our distance formula here. 4.9 t squared. Set it equal to 450. Okay, now we're going to solve it for t. So divide by 4.9. And then we'll take the square root. So t is going to equal about 9.6 seconds. Okay, so now let's take the 9.6 seconds, plug it into our velocity function. Okay, so this gives us approximately 94 meters per second. So that would be the speed when it hits the ground. Okay, derivatives. Okay, so we've seen that the same type of limit arises in finding the slope of a tangent line or the velocity of an object. Okay, limits of the form, okay, the ones that we've seen, arise whenever we calculate a rate of change in any of the sciences or engineering, such as the rate of reaction in chemistry or a marginal cost in economics. Okay, since this type of limit occurs so widely, it's given a special name and notation. Okay, the derivative of a function f at a number a denoted by, okay, this will be pronounced f prime of a, okay, is f prime of a equals limit as h approaches 0 of f of a plus h minus f of a all over h, as long as the limit exists. Okay, an equivalent way of stating this same definition is this version. Okay. The only thing I want to correct here is that this version should state x approaches a. Okay, we changed the h out with x minus a and some of the other notation. So this should say as x is approaching a. Okay, calculate the derivative at a general number a. Find the derivative of the function f of x at the number a. Okay, so let's take a look. If we're going to do derivative at a, that means we would have f prime of a equal to, okay, that same definition of the limit. We use the one with the h, limit as h approaches 0 of f of a plus h minus f of a all over h. Okay, so for this function we'll plug in a plus h everywhere there's an x. Okay, so limit as h approaches 0, a plus h squared minus 8 times a plus h plus 9 minus f of a, so a squared minus 8 a plus 9 all over h. Okay, one thing to just watch out for, the subtracting of the FA part. Okay, always put that equation in parentheses so that you remember to distribute the minus sign. Okay, so now you want to expand on the a plus h squared. You want to distribute the negative 8, distribute the minus sign, combine any like terms. So let's see what we end up with. Okay, so we have limit as h approaches 0. Expand on this, a plus h times a plus h, it'll be a FOIL. So that'll turn into a squared plus 2ah plus h squared. Distribute the negative 8, and that minus 8a minus 8h plus 9. Distribute the minus a squared plus 8a minus 9. Okay, so at this step, some things will cancel out. Okay, you guys will notice a squared and minus a squared. That's gone. You have a minus 8a and a plus 8a. Those are gone. You have, what else? A plus 9 and a minus 9. Those are gone. Okay, so we're left with 2ah plus h squared minus 8h all over h. Okay, factor out a h from the top. So we have 2a plus h minus 8 all over h. Okay, you can cancel out h from top and bottom. So limit as h approaches 0 of 2a plus h minus 8. Okay, apply the limit. H approaches 0. Okay, so then our general derivative at the number a would end up becoming 2a minus 8. And that will be the final answer. Okay, so another way to say the same thing would be f prime of a equals 2a minus 8. Okay, so another way to write the point slope form, okay, is with this formula. Okay, it's like y minus y1 equals slope x minus x1. Right, a and f of a, these are acting like our x1 and our y1. Okay, find an equation of the tangent line to the parabola x squared minus 8x plus 9 at the point 3, negative 6. Now, what we could do is use what we just found out. Okay, it's the same function. Right, this function is the same. We know what a is. Okay, a is 3. and we know what the general formula is for the derivative. Okay, so no reason to reinvent the wheel. So we plug in 3 into our derivative formula. Which gives us 6 minus 8, which gives us negative 2. Okay, so that's our slope. Okay, that's our derivative at a equal to 3. Okay, derivative is negative 2. So that's our slope. Okay, and we have our point. Okay, the point is 3, negative 6. So now let's plug into our formula. Y minus y1 equals mx minus x1. Okay, so y minus negative 6 equals negative 2, x minus 3. So this is a double negative, so y plus 6 equals, distribute, negative 2x plus 6, subtract 6 from both sides, so y equals negative 2x. And that would be the equation of the tangent line. Okay, rates of change. Okay, suppose y is a quantity that depends on another quantity x. Y is a function of x, and we write y equals f of x. If x changes from x1 to x2, then the change in x, also called the increment of x, is this, right? The change in x, delta x. Change in y is going to be delta y, f of x2 minus f of x1. And so our difference quotient would be, that's like our slope formula, right? y2 minus y1 over x2 minus x1. And this is the average rate of change of y with respect to x over the interval x1 to x2. Okay, in other words, it's our slope of the secant line in this figure. Okay, so by an analogy with velocity, consider the average rate of change over smaller and smaller intervals by letting x2 approach x1 and therefore letting delta x approach 0. Okay, the limit of these average rates of change is called the instantaneous rate of change of y with respect to x. Okay, and it's interpreted as the slope of the tangent to the curve y equals f of x at x1 f of x1. Okay, so instantaneous rate of change. We recognize this limit as being the derivative f prime at x1. Okay, we know that one interpretation of the derivative is as the slope of the tangent line to the curve when x equals a. We now have a second interpretation. The derivative f prime of a is the instantaneous rate of change of y equals f of x with respect to when x equals a. This means that when the derivative is large and therefore the curve is steep, the y values change rapidly. When the derivative is small, the curve is relatively flat, as at point Q, and the y values change slowly. Okay, and that goes back to our slope, right? The idea of slope. Larger the slope, it's steeper. The smaller the slope, it's flatter. Okay, speed. Okay, we have distance, the position function. Okay, is s equals f of t. Okay, f prime of a is the rate of change of the displacement. Okay, in other words, it's the velocity of the particle at time t equals a. Speed would be the absolute value of the velocity. Okay, so let's talk about this next example. A manufacturer produces bolts of a fabric with a fixed width. The cost of producing X yards of this fabric is C equals F of X dollars. What is the meaning of the derivative F prime of X? What are its units? In practical terms, what does it mean to say that F prime of 1,000 equals 9? Which do you think is greater, F prime of 50 or F prime of 500? What about F prime of 5,000? So the derivative f prime of x, we would define this as delta c over delta x. So it's the change in the cost over the change in the number of units. Okay, and so because we're taking the derivative, remember that we're going to be taking a limit. This will be limit as delta x approaches 0 of delta c over delta x. Okay, some places call this marginal cost. Okay, this would be the cost to produce one more item. Okay, so because delta C is units in dollars, in this case, and delta X is in units, the units would be dollars per, this is fabric, pardon, so this is dollars per yard. Okay, let's take a look at B in practical terms. What does it mean to say that f prime of 1,000 equals 9? Okay, so that means that basically this is our x value, so this means 1,000 yards of fabric Okay, 1,000 yards of fabric have been manufactured. The rate at which production cost is increasing is $9 per yard. Okay, so we would say production cost increasing $9 per yard. Okay, so the cost of manufacturing one more yard would be about $9. Okay, the next part. Which do you think is greater, f prime of 50 or f prime of 500? Okay, now generally the way it works is as you produce more, your production cost average tends to go down, right? Because you're probably going to be more efficient by producing more bulk quantity. Okay, so if you're talking about economics, the average production cost is probably less for the 500. This one's probably less. This one's probably going to cost more per item. Okay, because think about it. If you're paying people, if you're paying electricity to run the plant, rent, equipment, what have you, right? Fixed costs. It's going to cost you more per item to create 50 yards of a fabric versus 500 yards per fabric. 500 yards of fabric. Okay, and then for the F prime of 5,000, this is really up in the air. This may cost less, right, per yard. Okay, but it's also possible that maybe because you're producing too many yards of fabric, now extra stuff gets weighed in, like you'll maybe have excess overhead, you'll have overtime pay that you have to dish out to people working at the plant. So maybe the rate of increase of costs may rise. So it could be less or it could be more depending on what your argument is. Okay, derivative of a tabular function. Let dt be U.S. national debt at time t. The table in the margin gives approximate values of this function by providing end-of-year estimates in billions of dollars of debt from 1980 to 2005. Interpret and estimate the value of d prime of 1990. Okay, so d prime of 1990, this will be a derivative, right? So to calculate that, we would take limit as t approaches 1990 of dt minus d of 1990 all over t minus 1990. And so we could do this, right? We could figure out the difference quotient, right? The average rates of change for the various years, right? Just plug in these numbers into the formula, right? And get just average rates of change. Okay, so let's take a look at those. Okay, so these are our averages. So notice we don't have anything at 1990. Right? So what we could do is then estimate that it's going to be somewhere between 257.48 and 348.14. Okay, we're basically saying that we know that the debt isn't going to really fluctuate too much. It's not going to be many oscillation going on. we're going to calculate the average between these two, and that's going to be our debt. Okay, so we would just add these two. And then divide by 2. Okay, so this gives us 605.62 over 2. Which is about 302.81. Okay, so we could say that in 1990 we would have approximately $303 billion of debt per year. Okay, that would be the rate in the year 1990. Okay, so that brings us to the end of the lesson. Any questions, just let me know, email me, or bring it up in class. Have a good day, have a good night, we'll see you soon.